heat capacity, right? A solid material, when heated, experiences an increase in temperature, signifying that some energy has been absorbed, right? So there's a material, right? You are providing heat, all right? So this heat is absorbed by this material, and due to that, the temperature of this material rises, right? Solid material, when heated, experiences an increase in temperature, signifying that some energy has been absorbed, right? So you are providing some heat energy. Due to this material absorb that heat energy, the heat energy of the material is increasing. Heat capacity is a property that is indicative of a material's ability to absorb heat from the external surrounding. So heat capacity is a property that is indicative of material's ability to absorb heat, right? So material, how much heat it can absorb is indicated by the heat capacity from the external surrounding. So external surrounding means you are providing some heat. The heat is not generated by the material, but you are providing some heat. Heat represents the amount of energy required to produce a unit temperature rise, right? So unit temperature rise, for in calculations, we will say at unit mass, unit temperature rise, the energy needed is the heat capacity, right? In mathematical terms, the heat capacity C is expressed as follows. C is equal to dq by dt. So the change in the provided energy dq divided by the change in the temperature dt is known as the C, right? That is the heat capacity, where dq is the energy required to produce a dt temperature change, right? So dq, this is the heat energy, and dt, this is the temperature change, right? Ordinarily, heat capacity is specified per mole of material, right? So heat capacity is specified per mole, that is joule per mole Kelvin, right? So this is a usual notation. Joules, that is energy, per mole Kelvin. This is temperature measured in Kelvin, energy measured in joule, and this is for 1 mole of substance. So the unit is joule per mole Kelvin. The specific heat often demonstrated as log S. Okay, specific heat is sometimes used. This represents the heat capacity per unit mass. Okay, so here the unit mass thing is not there for heat capacity. When it is coming as specific heat capacity, right? When it is coming as specific heat capacity, we have that unit mass thing, right? Unit mass. All right. So there it will come as joule per kilogram per Kelvin. So here it's per mole, right? This is the amount of the substance. But when it comes to specific heat capacity, that is joule per kilogram Kelvin, right? That is joules per kilogram Kelvin. All right. So this is the difference between specific heat capacity and heat capacity. These are no same terms, right? These are different terms. So this is a like sample diagram of how this transforming of the heat is occurring. Normal lattice positions for atoms, right? So these orange, these are normally how these lattices are placed in a particular material. Then positions displaced because of vibration, right? When you provide some energy, that gains some energy, right? If you provide some energy, each atom will gain some energy, right? So once it gain energy, what will happen? It won't stay at a place, right? That will start moving here and there. So exactly like you guys, okay? Say for example, you are there in your hostel rooms, okay? And if you are provided with some money and go to buy things, what you will do, since you have extra money, you will run out and buy the stuff, right? So which means if you have extra energy, you can't stay at that place. So the case is similar for atoms also. If we give some extra energy, they can't stay at a place. What they will do, they will start vibrating here and there, and while they are vibrating, they will transfer the energy from one atom to other atom, right? So that is a kind of chain reaction. So that will travel throughout the material. So here you see schematic representation of the generation of the lattice waves in a crystal by means of atomic vibrations. So actually these orange spots are the spots where the electrons should stay. Due to you provide some energy, see some of them are going there, some of them are moving this way, right? So this region is kind of less dense and this region is more dense. Right? So they are kind of vibrating. So they won't stay at a place, they will vibrate all the atoms. There are two ways in which this property may be measured according to the environmental conditions accompanying the transfer of heat. Right? So this C, that is heat capacity, can be measured in two ways. One is the heat capacity while maintaining the specimen volume constant, right? That is named as CV, right? That is CV. So C is the heat capacity and V is the at specific volume. So this is heat capacity at specific volume, right? Heat capacity at specific volume, or volume is constant, right? Similar way, there is a CP also, right? CP, that is heat capacity while pressure is constant, right? Pressure is constant. The other one is constant external pressure, which is denoted as CP, right? This is our CP, right? This P is for constant pressure, right? So this P denotes constant pressure, heat capacity, and this one, first one, denotes constant volume, heat capacity, right? So what is this constant volume heat capacity means? You have a particular volume, right? Say this is V. You are putting some material inside and you are providing heat, okay? When you provide heat, what will happen? Vibrations increase, right? They will not stay at a place, they will run here and there and collide with others and energy will be increased. So due to that, what will happen? Pressure will be increased, right? Pressure will be increased, okay? So while having the volume as constant, right? While having volume as constant, what is happening is pressure will be increasing, right? Pressure will be increasing. CP means you have a container, okay? You have a container, okay? This is a lid, okay? So here I have some molecules, all right? Molecules are there and you are providing heat, okay? So this I told you CP, all right? So here the pressure is constant, which means when you provide heat, these particles will start move here and there and collide with each other. So which means pressure is increasing, right? As like here, pressure is increasing. In order to manage that increase in pressure, what will happen is this lid will start moving up. So this is not a tight lid, this can move up and down. As like you have a roller door here, right? When the pressure increases, this lid move up, right? So once you provide like energy, right? Energy, efficient energy at a stage, say for example, that is ended up in this place, okay? Say for example, that is ended up in this place, right? So due to all these collisions, what will happen is actually it was there at the beginning, right? After all these collisions finished, this is moving upward and ended up in here. So here you see initial volume was this much, but the final volume is this much, which means volume is increased, right? Volume is increased, but the pressure is constant. Why? This is allowed to move freely, right? So if there is excess pressure, this can move up. If the pressure is low, this can move down, right? So it can keep the pressure constant, all right? So this would be the setup of the constant pressure heat capacity, right? This is how a constant pressure heat capacity works, right? Okay. So when the volume is constant, pressure will increase. When the pressure is constant, volume will be increased, right? So this is a like vice versa formula. If you want to keep one constant, the other one anyhow should be increased, right? So if you keep the pressure constant, volume is increasing. If you keep the volume constant, then pressure is increasing, right? So this is one is constant pressure heat capacity, and the other one is constant volume speed capacity. Constant external pressure, which is denoted as Cp. Okay, so this is the other one. The magnitude of Cp, right? Magnitude of Cp. What is that Cp? Constant pressure heat capacity is almost always greater than that Cv, right? Cv is constant volume heat capacity, right? So this Cp is almost greater than Cv, right? Almost a little bit. However, this difference is very slight, right? Very slight for most solid materials as at room temperature and below, right? So most of the solid material, why this is slight, I mean this difference is very low is solid material, you know, the increase in volume would be little bit, not little bit actually, when compared to gas and liquid substance, the volume change of solid material is very low, right? So again, you can imagine, right? When you take a balloon and input the gas, right? Volume is increasing like this fast, right? Similar way, when you take some milk and cook it in the fire, what will happen? Initially milk will like this, then at some stage it will come like this, right? So for gas state, that is balloon, right, example, and liquid state, that is this milk, the volume change is kind of significant, right? But in the case of solids, the volume change is very low, right? Why? The thermal expansion of coefficient that we will study in the later stages, right? That is like in the power of 10 to the power minus 6, minus 5, something like that. So the change in the volume or length or area would be very less for solids, particularly for solids. So this is why for most solid materials at room temperatures and below, the difference is slight, right? Cp is greater than Cv, that's true, right? But the difference between Cp and Cv is very, very low, okay? Temperature dependence of the heat capacity, okay? Temperature dependence of the heat capacity. Variation with temperature of the vibrational contribution to the heat capacity is a constant at constant volumes for many relatively simple crystalline solids is shown in the figure. So there's a figure, okay, below, right? Cv is 0 at 0 Kelvin, but it rises rapidly with temperature. So here, Cv is, specific heat capacity, heat capacity at constant volume. So at 0 Kelvin, right? At 0 Kelvin, this is again 0. So if you start to a graph, if you take this as Cv and this as this as temperature, x-axis, and this as Cv, starting point would be here. That's fine, right? But it rises rapidly with temperature. This corresponds to an increased ability of the lattice waves to enhance their average energy with ascending temperature. So this is the equation. At low temperature, the relationship between Cv and the absolute temperature T is AT cube, right? What will happen is this will rise like this fast. Why? That is AT cube. So at 0 temperature, right? Temperature is 0, Cv is also 0. That's fine. Why? If you put T0, C is also 0. Okay. What will happen if you put T1? 1 cube is 1. You keep the A, that's a constant, no? So we'll keep it. And Cv is also 1. When you put 2 for T, C would be 2 cube, that is 8. If you put 3 for T, Cv would be 3 cube, that is 27, right? So your values will be 0, 1, 8, 27, something like that. So 0, 1, 8, 27, then 64, right? 125. This will be going like this. So this is the way the temperature relationship between Cv and the absolute temperature. right? Where A is a temperature independent constant, right? So this A is a constant which does not have anything to do with the this temperature or with the gradient, right? This does not have anything to do with that. So CV, it's dependent of the heat, dependence of heat capacity at constant volume on temperature at low temperature 0 Kelvin. So it will start at 0, 1 and will end up in like 8, 27, 64. So just imagine if you increase the heat from 0 to 10, the temperature difference is just 10 Kelvin. Okay. If you increase it from 0 to 10, temperature difference will be just 10 Kelvin to heat capacity. That will be like cube of that. That is 10 into 10 into 10. That is 1000 into a is a general number, right? So that's 1000. So the heat change is very huge, right? So this is a like rough explanation what is actually happening. Energy absorptive mechanisms are also exist that can add to the total heat capacity of a solid. Okay, so what are the mechanisms that will actually contributing to this phenomena? In most instances, however, these are minor relative to the magnitude of the vibrational contribution, right? So the contribution could be minor, but there's an electronic contribution in that electrons absorb energy by increasing their kinetic energy. So as I told you, if you provide extra energy, they will get it and increase their kinetic energy. When the kinetic energy increases, they won't stay at a place, they will start moving here and there. However, this is possible only for free electrons, those that have been excited from filled state to empty states above the Fermi energy level. Right? So here are four terms, right? Four terms. One is our CP, other one is CV, then K, then L. Right? So first one is the CP. Okay. So this is heat capacity at constant pressure. So usually we go for CP, right? That is joule per kilogram per Kelvin, right? Joule per kilogram per Kelvin. And here we have alpha. Alpha, I told you, thermal expansion coefficient, right? Thermal expansion coefficient, which means whenever you provide extra heat, right? Not extra heat, whenever you provide heat energy, I told you there will be some increase in the length or area or volume, right? So that is this alpha, that is thermal expansion coefficient. That's you see in the range of 10 to the power minus 6. So this is why the change in the volume or length or area is very, very small in solids compared to the liquids and gases, right? And then we have K, that is conductivity, that is watt per meter Kelvin, right? Watt per meter Kelvin. So aluminium heat capacity is 900, then copper 386, gold 128, iron 448, right? There are few alloys also. Brass, that is 70 copper, 30 zinc 375. Covar is there 55 feet, 29 nickel 460, right? These all are heat capacities. Then I have alpha, that is thermal expansion coefficient, right? So there, if you see, aluminium has the highest thermal expansion coefficient, and silver, that is 19, right? Also, we have brass, that is around 20, right? So these are the metals that can have a kind of at least little bit higher thermal expansions. All right. When you compare these metals with these ceramics and polymers, right? This area with this and this, ceramics you see here, the heat capacity almost there in the same range, right? 700, 900, 700, 700, 800, 800, right? So silica, spinel, magnesia, alumina, soda, lime, right? Borosilicate, while their thermal expansion coefficient is very low. Very low in the sense compared to these metals, that is low. So alumina is 7.6, magnesia 13 point, right? And 7.0.9 point. All right. So a general term is the heat capacities of metals, right? And ceramics can be a kind of comparable, while in the case of alpha, that is thermal expansion coefficient, these terms, right? These terms, that is not terms, values. Thermal expansion coefficient of metal is a little bit higher than the ceramics, right? And further, if we compare it with polymers, right? Polymers have CP high, right? And they have the thermal expansion coefficient also high, right? Very high. So from this chart, what you can understand is you need to provide like less energy for these metals to increase the temperature, specifically for gold, silver, tungsten, right, brass, right. So you need to provide less heat to increase the temperatures. If you compare these three, right, metals and ceramics and polymers, polymers are the materials which need high amount of heat energy to change their temperature from one value to other. They need see 800, 1850, 1920, like that, right? So polymers are the materials which need high amount of energy to change the temperature by a unit value, while metals, and in metals particularly gold, silver, tungsten, these metals need less energy to change their temperature from particular degree Celsius to particular degree Celsius. That's a kind of unit, right?